All right, good morning. I hope you're enjoying your day off, and I apologize that we have to do the presentation this way, but I hope you like having a little bit of snow, and I'll try and keep this under 30 minutes and see if we can't get through it. This is AP Calculus. This is the presentation for section 4.6. I am Mr. McCully, so if you found this video, you've got the right one. Let's get started. Yesterday I finished up section 4.5. There was a portion that I did not get to that I would like to do. It is using a change of variables to evaluate the definite integral, and that's what we're going to be doing here. So here we have a definite integral, and just like yesterday, we looked for the inner portion, the function. We have composition here, and we're looking for the inner portion of that set of composed functions. And I look at that, and I do let 2x minus 1 be my u, and that's what I'm going to do my substitution with. And then, just like yesterday, we're going to derive this section so that we can replace the dx. And I say, all right, du is going to be equal to 2 dx. Now, the problem arises is this variable expression right here. I have my 2 dx, but I have this extra x that I have to deal with. And since I'm changing my variables again from x to u, this part is a problem. When you come to this type of problem, there is a way around it. You can do a complete change of variables. So the way we're going to deal with this little extra x is we're going to say, all right, if u equals 2x minus 1, if I solve for x, add the 1 to both sides and divide, I'll get x is equal to u plus 1 all over 2, or equal to a half u plus 1/2. And then dx is going to equal the derivative of this expression. Now the derivative of this expression is just 1/2, and since that's a constant, we're done. And that makes sense. If I told you to solve this for du, or solve this expression for dx, you divide both sides by 2 and you get dx is equal to a half du. All right, so now here we're ready to start doing our full substitution. So I'm going to substitute the x with my new x expression, which is this. So 1/2 u plus 1/2. And then I'm going to change this radical to a rational exponent, so a half. And then I'm going to substitute this expression right here with u. So I have my u there, and then changing my dx is equal to 1/2 du. So now I've completely changed all of my variables. Now the only thing that happens here, we're changing our variables. This is my lower and this is my upper bound for the variable x. So I have to have a new lower bound and a new upper bound for the variable u. That's fairly simple to get. All we're going to do is we're going to plug these two numbers into here. So if I go 2 times 1, the lower bound, minus 1, I get 1 again. So my new lower bound is 1. And then my upper bound is going to be 2 times, and I'm going to take this 2, plug it in for u, minus 1, it gives me 3. So my new upper bound is 3. Hopefully that's not too bad. Now, just to make this a little easier on myself, I see that this expression has a factor of a half. I've got a half for my du here. So just to make it a little bit nicer numbers, I'm going to factor out a half here, put it out front, factor out a half here, and put it out front. And so a half times a half is a fourth when I factor that out. Still have my integral of 1 to 3. When I factor out a half from both of these, I'm just left with u plus 1. This thing doesn't change, it stays the same. I've got my u to the 1/2. Factor out my half there, and so I just have du. Now I'm going to finish this integration. I'm going to go to 1/4 integral from 1 to 3, and then it's at this point that we really see the power of using this change of variables. Now, since this is to the first power, I can distribute this u to the 1/2 to both of these terms. That'll give me u to the 3/2 plus u to the 1/2 du. And now I can integrate these two expressions using the simple power rule separately. So completing the integration here, I now have u to the 3/2 plus 1 over 3/2 plus 1. I didn't want that quite yet. Let's see if I can get rid of it. Did the whole thing. Darn it. Sorry about that. 3/2 plus 1 plus u to the 1/2 plus 1 over 1/2 plus 1. And that's going to be evaluated from 1 to 3. And so I'm not going to finish the computation here. I'll let you do that to get u to the 5. You know what? Let's get rid of that and do it one more time. 1/4. And this is going to be 3/2 plus 1. 3/2 plus 2/2 is 5/2. We're dividing, so we flip it. 2/5 u to the 5/2 plus 1/2 plus 2/2 is 3/2. Since we're dividing, we flip it. 2/3 u to the 3/2 evaluated from 1 to 3. So you just plug in 3 into this expression and then plug in 1, subtract those two, multiply by 1/4, and there is your definite integral. Just trying to keep it short here. All right, so when you're doing guidelines for change of variables, choose a substitution for u. G of x is usually best to choose an inner part of a composite function, which is what we talked about yesterday. You're going to compute du by finding the derivative of whatever we call g. Then we're going to rewrite that integral in terms of u, and then we're going to find the resulting integral in terms of u. Now, if you're doing indefinite integrals, we'll do 5 and 6. These are for indefinite integrals. When you get done doing that integration, replace u with g of x to obtain the antiderivative in terms of x, and then check your answer by differentiating. This is always an optional step here. We know that if you're unsure about your integral, just take the derivative, and if you get your original function, then you should be okay. All right, that's enough of that. Moving on to section 4.6. There are only two real things that we want to talk about today for this section is the trapezoidal rule. This section also discusses the Simpson's rule, but please keep in mind that you do not have to do the Simpson rule for the AP Calculus test, so I am going to omit it from our class. Simpson's rule is similar to the trapezoidal rule. It's a little bit more challenging, but for the purposes of this class, anytime in the homework it asks you to do the Simpson's rule, just throw that portion out. So I'm cutting that out of the homework, okay? So, and then we're going to talk about finding how much error there is when you use the trapezoidal rule to approximate that integration. Okay, so the trapezoidal rule approximates the area under the curve over a given interval. And since it is an approximation of area under the curve, it's also an approximation of the definite integral. Those are two similar concepts, and it comes down to this: is if f is a continuous function over the interval a to b, then the definite integral can be approximated by this expression. This is nothing more than an extended version of the trapezoidal area equation, which we remember to be a equals 1/2 the base times b1 plus b2. You're going to see that this 2 is part of that half. This is not a little b. I didn't make, oh man, that's too big. A equals 1/2 the height times b1 plus b2. This little 2 here is going to be your half. B minus a divided by n is going to be your h, and then this expression is all of the bases, because we're going to have a bunch of trapezoids next to each other. So this is a simplification of all of these bases that we're going to end up with. And then n, this n here, is going to be the number of intervals over to a to b. So let's see what that's going to look like. So let's say I have some interval a to b, and that's not very good. Let's see if I can't do a little bit better one. This is not my normal pad, and I'm sitting at my desk today, so This is what we're going to work with. Okay, so here's my a to b, and just to keep it simple, we're going to find 3 intervals here. So our n is going to be equal to 3. Let's use some lines, and while I'm at it, might as well call this, here's my function f of x, and so there's my first one, and since we're dividing it into 3, let's see if I can't make those look pretty close. Those are pretty close to equal. Alright, so essentially what I'm going to do here is I'm going to create 3 trapezoids. Now already you can see that this approximation is going to end up being pretty darn close. It's a pretty good approximation. We can only see a little error here, there's a little error there, and the way that we're going to do this is, look, how would you figure out how long each of these are? And remember, these are the parallel sides, so these are your bases, and each of these are going to be a height. Now these heights are all going to be the same length, and we're going to calculate them. Well, how do I figure out how long this distance right here actually is? Well, it's from to get a to b, we're going to go b minus a. That's going to give us the positive distance from these two things. And since we're dividing it into 3 sections, divided by 3. That's how long each of these sections are, b minus a all over 3. Now if we go back to that equation, b minus a divided by 3, now the 2 comes from this half. So if I want to figure out how tall, these are my bases of the trapezoids. So if I want to find out how tall they are, I would plug in the value. So what we're going to call is we're going to say this is x0, this one here is x sub 1, this one here is x sub 2, and this is going to be x sub 3 or x sub n. So how do I figure out how tall that base is? Well, I plug in this x value into the function. So this is f of x sub 0. This one is f of x sub 1. This is f of x sub 2, and this is f of x sub 3. So, if I'm calculating this first trapezoid, I would get that area is equal to 1/2 the base, which is b minus a divided by 3, times these two expressions. So I've got, let's see here, f of x sub 0 plus f of x sub 1. Those are the bases of this first trapezoid. The second trapezoid is going to have a similar height. It's going to be the same. So it's 1/2 b minus a all over 3. And this time I'm going to use this base here and this base here because I'm finding that middle trapezoid. So f of x sub 1 plus f of x sub 2. And then my final trapezoid will have an area of 1/2, and then it has the same base, b minus a all over 3. And then its area, or its bases, are f of x sub 2 plus f of x sub 3. Now, if you notice, I've got 1, 2, 3 terms, and I'll try and highlight those right here. I've got this one, got this one, and I've got that one. And all 3 of those have an expression of this 1/2 b minus a over 3. So if we go back, notice, basically it looks like I factored all that out and I put it out front. And that's what I'm going to do here. So let's go back here. If I factor that out, I've got 1/2 b minus a all over 3. And I factored that from this one, and this one, and that'll leave me f of x sub 0 plus f of x sub 1. So that's this expression right here, and I've basically taken care of that. Can't really cross it out, but let's use a highlighter and say I've already crossed these parts out right here by factoring out of the whole thing. And now this expression is gone because of that. And so now I'm going to add here, so f of x sub 1 plus f of x sub 2. And now I have taken care of this portion. And so that's right there. And now I'm left with this. So f of x sub 2 plus f of x sub 3. And you'll notice, if I put that up just a little bit, that the f of x sub 1s and the f of x sub 2s have been repeated. So if I bring my 2 over here, I got b minus a over 2 times 3, and then it's f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 plus f of x sub 3. So this is a specific example, and they generalized it here. So if you notice, these 2's here, 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 oh shoot, I've got an error. Sorry guys, this is incorrect. Let's just cross that out. That shouldn't be there. Sorry about that. I'll try and fix it before I put it on the put my notes up on the web so that that one's correct. All right, there should be no f of x. There should be no 2 there. There's only the 1. And the reason that is because when we add up all these outside values here, this expression here and this expression here, those things are only used one time. Whereas because when we calculate the area of this particular trapezoid, we use this side, and we calculate the area of the middle trapezoid, we use that side again. That's why we end up with 2 for those middle values, because we use f of x of 1 twice and f of x of 2 twice in this particular one. And then if you had 4 intervals, the inner sections would be used twice, where these outer lengths are only going to be used once. Okay. Let's do a specific example and see if I can do it without screwing up. So I am looking on page 316, number 4, and they ask us to do the definite integral of from 2 to 3 of 2 over x squared dx, and they want us to use 4 sub-intervals. So we need not an n there, we need a 4. Okay. All right, so with this thing, the way I'm going to do it is I'm just going to use that equation that I have here, now hopefully corrected, and we'll go back and forth. So my lower and upper bounds are, so we're going to go 3 minus 2, and then 2 times my n, which is 4. So do that. And now we got to figure out what these values on the inside are. So I don't have a graphing calculator application for this this computer at home, so I'm just going to calculate them using my graphing calculator off the side and plug them in. But essentially what we're going to end up having to do here is go through, and since it's only from 2 to 3, and I got 4 values, I'm going to have an x sub 0, I have an x sub 1, an x sub 2, an x sub 3, and an x sub 4. Now the outside values are easy because there, if we remember from here, there are our outside values are going to be a and b. So when I plug these ones in, I've got 2 here and I have 3 there. Now I just have to find the values in between. Well, if I divide the difference between these two into 4 parts, I'm dividing them into quarters. So this is 2.25, this is 2.5, and this is 2.75. And then the difference between each of those two is 1/4 or 0.25. So those are my x values. They went a little too high there, so let's move this whole expression down. All right, so this is going to be f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 plus 2f of x sub 3 plus just f of x sub 4. remembering that your outside two values only have a coefficient of 1. All the inner ones have a coefficient of 2. So I'm going to go through and quickly calculate these things. And I'm going to use my graphing calculator off to the side. I wish I could show it, and I apologize that I can't. But, hopefully, if this ever happens again, I'll get my calculator, x sub 2 and f of x sub 3, f of x sub 4. And I'm just going to make a table. It shouldn't take me too long here. The equation is 2 divided by x squared. My table set up. I'm going to start my table at 1, or actually I need to start my table at 2 and go by 0.25. If I do it as an auto, it's going to bang them out pretty quick. F of x sub 0 is 0.5. F of x sub 1 is 0.395. F of x sub 2, or f of what's going to end up being 2.5, is 0.320. X sub 3 is 0.264, and then is 0.222. So doing this calculation, I get 1 over 8, and then I got 0.5 plus 2 times 0.395 plus 2 times 0.320 plus 2 times 0.264 plus 0.222. All right, so 1/8 times, and I'm just going to calculate this expression here real quick. 0.5 plus 2 times 0.395 plus 2 times 0.320 plus 2 times 0.264 plus 0.222. I get 1/8 times 2.68, and so when I divide that by 8, I get 0.335. That's my approximate value now. I'm not going to go back and check my work just because I'm already at 22 minutes, and I said I'd try and keep it under 30. But my process is correct here. The only thing that I would have made a mistake is somewhere in my arithmetic, and we all know that Mr. McCulley often makes arithmetic errors, so you might want to check that before you move on. All right. Finally, right? Last thing. Error approximation for the trapezoidal rule. This equation here calculates the error that is in your trapezoidal rule, how much you're off by. And it's fairly straightforward. This is the upper bound, this is the lower bound, this is the number of intervals that you have. This is an expression that we haven't really seen yet before. And basically what it says is that over this given interval, they want to know what the absolute value of the maximum value that comes out of the second derivative of whatever your f of x is. So if I wanted to calculate the amount of error that I had here in this expression, I would take the second derivative of this thing, take the second derivative of that thing, figure out what the maximum value of that second derivative was over the interval from 2 to 3 and plug that in here, and then just make that calculation. So just real quickly showing you how to do that, we said from the last expression f of x was equal to 2 over x squared, and I need to check that just to make sure. Yeah, 2 over x squared. So if I take if I rewrite this as 2x to the negative 2, the first derivative of that would be equal to negative 4x to the negative 3, and then the second derivative of that would be equal to negative or no, it's going to be positive now, 12x to the negative fourth. Now, this expression, I got 2 over x to the x to the fourth. Here's the thing. I know that the graph of this thing is going to look like this. And you guys all know it too. It has an undefined 0, and since the degree of the numerator is higher than the degree of the denominator, it has y equals 0 as its horizontal asymptote. And so it's going to start up there and descend. So if we're talking over the interval from 2 to 3, the highest value for this particular one, and it's not always going to be true, you may have to look for it, this just comes out being equal, the highest value is obviously going to be at 2. It just is. So when I calculate this error, it has to be less than or equal to, and again, we're approximating the error. It's going to be, the upper bound was 3 minus 2 to the third over 12 times, and we had, what do we have, 4 intervals here, so 4 squared, and then the maximum of this value would be the absolute value of f double prime of 2. And we'll calculate that here in a moment. So I get 1 over 12 times 16, and let's see here, 2 to the fourth, 2, 4, 8, 16, got 12 sixteenths. That is the value of the second derivative, f double prime at 2. And so that is the maximum value, so 12 sixteenths. And so my error, and I'm going to calculate this on off to the side here. So I've got, it's essentially 1 over 16 squared. Oh, come on, luckily you can do that in your head. 1 over 256, which is 0.0039. That's how much I'm off by. Actually, it has to be less than or equal to that. That's the biggest, that's the most I'm going to be off by. So the error is less than or equal to this. All right, that seems to be just about it. I kept it under 30 minutes as promised. If you have any questions, you know my email. Go ahead or leave a comment in the section below. Thank you and have a great day.